in lesson 3.4, we're looking at exponential and logarithmic models. There's 5 common exponential logarithmic models. We've got exponential growth and decay, we've got the Gaussian model, a logistic growth model, and a logarithmic model. And then here are what the graphs of these models would look like. All right, so we've got an example 1 that talked about bacteria that has grown from 40 to 326 in 120 minutes. And they want us to find the growth formula. So what we need, if we're looking at exponential growth, it's written like this, but this is really just y equals pe to the rt. Sometimes r is a k value. They all use different letters, so k is really just talking about r. So if you think about PERT, we've got y equals pe to the rt, and they say it's 326 bacteria, started at 40, 120 minutes has gone by, and they want us to figure out what r is to make the growth formula. So we're going to divide by 40 first, and we get 8.15. And then we want to get the r and the 120 out of the exponent. So we're going to do natural log. And then divide 120 to the other side. So r is 0.01748, or k in what they're talking about. So if I'm going to write my equation, then the formula is y equals the starting amount times e to the 0.01748 t. So they asked for a formula, which is what we just did. So I've got an input and an output. You input the amount of time, and it'll tell you how many bacteria there are at that many minutes. So we've created the formula given the starting amount and the growth constant. Now we're going to use that formula to figure out how much bacteria there will be in 240 minutes. So we're going to plug 240 in for the t. Okay, so plug that into your calculator, and you should get about 2,654.68. So that's how many bacteria will be there in 240 minutes. Example 2, they've given you the formula, and they're asking you to use it. So it wants to know how many insects are going to be there at time 500. Well, you see y equals pe to the rt. 500 is your starting amount, so it's 500. If you don't know that, you can plug in 0. You're going to get e to the 0, which is 1, and 1 times 500 is 500. So 500 is the starting amount. What's the population at 10 days? So we're going to plug in 10 to the equation. And you type that into your calculator, and you're going to get 610.7 bees. And then when will the population reach 800? That's asking it a little bit backwards. So when, they're looking for time. 800, they're giving you the end amount. So you've got 800 equals 500 e to the 0.02 t. We're going to divide 500 to the other side, and we get 8/5. Then we're going to get rid of the e and do natural log. And then we divide by the 0.02. And we get 23.5, and we're measuring this in days, so days. So it'll take 23 and a half days to get to a population of 800. In example 3, we've got exponential decay, and we're looking at half-life problems. So the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to become disintegrated. The half-life of radium is 1,690 years. If 10 grams is present now, so 10 now, how much will be present in 50 years? So they're giving you two different times, which can be a little confusing. So you use the first time to figure out your rate of decay. And then once you know it, you make an equation and then plug in the 50. So it's all the half-life problems are really two-step problems. So we can use this PERT equation. And we know that it starts with 10. And we don't know the growth rate. We know we're going to have half of the substance in that amount of years. So we can plug in 1690 for t, and we're going to have half. So if I'm starting with 10, that means I'm going to end with 5, half. So if I divide by 10, I'm going to get 1/2 because it's half-life. And then we are going to get rid of e, get this out of the exponent by changing it into a logarithm. So it'd be natural log 1/2 equals 1690r. And then you divide by 1690, and r is negative 0.00041. So that means my equation is y equals 10e to the negative 0.00041 t. This is my formula for the half-life of the substance. And now that we have the formula, we can plug in the 50 for the time. So you multiply by 50 in the exponent, and you should get approximately 9.8 grams is how much will be left, which should make sense. If it takes that long to get to 5 grams, and we're only letting it decay for 50 years, then we shouldn't have lost that much. Example 4, we've got a decay problem. They've given you the function in the problem. And they want to know how much is going to be left at 10 years if we're starting with 500. So a sub 0 is the initial amount. So we plug in 500 for a sub 0. And it's letting it decay for 10 years. So we're just going to plug in 10, and you type this into your calculator, and you should get 391.74 grams. When will 400 grams be left? So when, they're asking for time. They're giving you the end amount. So we're going to set 400 equal to 500 e to the negative 0.0244, and t is what we're looking for. So you want to divide by 5 first, and you're going to get, or 500 first, and you're going to get 4/5. Then you want to get t out of the exponent, so you're going to do natural log of both sides. And then you divide by this negative 0.0244, and we get 9.15 years. So it takes about 9 years to get to 400. What is the half-life then? So set it equal to 500. And if it's half of it, so then that means we're going to get to 250. And half-life is asking for time. Half-life is time, how long it takes to get to half. So we're solving for t. Divide by 500, and you're going to get a half, because we're looking for the half-life. Change it into a logarithm. And then divide by the negative 0.0244, and we get t to be 28.4 years. That's how long the half-life of this substance is. Here we've got Gaussian model. We're talking about the SAT in 2001. It says it was normally distributed by this equation from 200 to 800, where x is the SAT score for mathematics. Sketch the graph of the function and estimate the average SAT score. So if you graph it, and you're going to have to fiddle with your window a lot, you have a really large x span, but a really, really small y span, and then you end up seeing this bell-shaped curve. And when you're looking for the average in a bell-shaped curve, you're looking for that 50% of the data, so halfway through the curve. And we see in this function that it's at 514. So that is telling us that half the population was above or below 514. So we can say 514 was the average score in 2001. On the next example, we've got logistic growth model, and they've given us an equation to describe the spread of a virus on a college campus. Um, and they want to know how many students are going to be infected after 5 days. So they give me this equation with t as a variable, and we're just going to plug in 5 into the equation for t so that we can find out how many days it would take. So we take the equation, point 8, and then we plug in 5 for the days. So you plug that in carefully on your calculator, and you're going to get 54 days. No, 54 students, because we plugged in 5 for the days. So 54 students will be infected after 5 days. Then it wants to know, after how many days will the college finally cancel classes? And it said up here that if 40% or more of the students are infected, then they will cancel classes. So first, let's think about what's 40% of the student body. So if we take 0.4 times the student body, which is 5,000, we get 2,000 students. So 2,000 students would be 40%. We're going to set this equation equal to 2,000. And so we've got all this stuff on the bottom. The first thing we want to do is multiply all of that to the other side. So we multiply all of this to both sides, and then that cancels it. So I'm going to have this times 2,000 equals 5,000. Then we are going to divide the 2,000 to the other side. And we get 5 halves. And then we're going to subtract 1 to the other side. And we end up getting 3 halves. And then we divide by the 4,999, and I'm going to stop doing fractions now. And we get 0.0003 approximately. And then I want to get rid of my e, so we're going to change this into logarithmic form. So it'd be natural log of 0.0003 equals negative 0.8t. And so if you do the natural log on your calculator of that number and divide by negative 0.8, you end up getting 10. 10.13. So about 10 days it would take to get to 40% for this virus. And we use logarithms to talk about earthquake intensity. This is how you would figure out the Richter scale magnitude of an earthquake. And so what you do is you plug in you plug in 1 for the minimum intensity, and then you plug in your Richter scale rating for R, and you're able to find the intensity of the earthquake. So that's what we're doing here. You plug in 1 for I sub 0, plug in 8.3 for the R, and I just changed it into exponential form. So 10 to the 8